Okay. We're going to talk today about depletion PVT tests, which are conducted for reservoir fluids, gas condensates, and oils. Today we'll make it through the oil test, the differential liberation test, which is covered in some detail in Chapter 6, and the entirety of Appendix D is dedicated to discussing the oil tests, the differential liberation experiment. Now, Appendix D also includes the manner in which the differential liberation test and the multi-stage separator test, which I refer to as SEP, that's multi-stage separator test, are combined to yield the so-called black oil PVT properties used in very many of the petroleum engineering applications, engineering and reservoir production engineering, namely the oil formation volume factor, the solution gas oil ratio, and the gas formation volume factor. And in the case of this discussion in his Appendix D, the particular type of gas formation volume factor that he's discussing is what will be referred to in Chapter 7 and in these lectures about black oil properties as the BGW, the so-called wet gas formation volume factor. So combining the differential liberation test data and the separator test data into the so-called, and really this is the way it's done, it's being combined and to calculate these three properties, which is called the not simplified, but the traditional black oil PVT properties. And all of this is leading up to the next topic of discussion, which is in Chapter 7, the title of which is Black Oil PVT Formulations. And in that Chapter 7 on black oil PVT formulations, there are basically two types of black oil models, if you will. The one being this traditional, which is discussed in Appendix D and used for the most part in all of the reservoir and production engineering textbooks. So it's the most common, at least historically, the traditional black oil. But that applied basically up from, let's say, whenever they started using black oil properties. I can't exactly tell you, probably sometime in the 50s up until around I'm going to say 1980, but it was mid-80s, late 80s. I'll just put 80 here. And then what happened is that in the 70s, one started drilling deeper and deeper, finding reservoirs with higher and higher pressures. You started finding reservoirs that had more and more gas in solution because of the higher pressures. So you had oils with very high gas content, and those oils might behave like gases, very rich gases, or very volatile oils. And this trend in the 70s to go to deeper, the price 74 oil crisis, the price of oil went, sky high. So people spent more money drilling deeper. You found higher pressure reservoir fluid systems that contained a lot more gas. And that gas, either in solution or free gas, contained, when it came to the surface, it flowed as gas in the reservoir, but when it came to the surface, it carried with it a lot of what ended up being stock tank oil or condensate. It added a lot of value. So after the 1980s, we have what's referred to as the modified black oil PVT model. And that tries to treat the importance of the oil or condensate that can be dissolved in a reservoir gas and carried with that reservoir gas, which when produced to the surface yields a substantial amount of very valuable oil. Okay? Before 1980, effectively, we said that any gas in the reservoir yielded zero condensate at the surface. And that was the assumption made, for example, in the first major, and I think still the second largest oil field in Norway, which was the largest being Statfjord, the next largest being Ekofisk, which was the first major discovery in the North Sea of oil. And that field was at high pressure, about 7,000 psi, which is, I don't know, however many bar, divide by 15. And it contained about 300 standard cubic meters of gas in solution in the oil. Okay? And when that reservoir started depleting and the gas came out of solution and started flowing faster than the oil, it carried with it a substantial amount of condensate. In other words, the oil transformed into gas, came out of solution, but that gas itself contained a significant amount of what became oil at the surface. Now that was ignored in the initial calculations in the late 1960s and early 1970s by Phillips Petroleum Company and their co-operator or co-owner Petrofina, major co-owner. And they did depletion recovery calculations of oil from this 6 billion barrels of oil, which was a lot of oil, and it still is a lot of oil. You don't find these kind of reservoirs much at all anymore. And the recovery factor, ignoring just that issue, using the traditional black oil tables, using the methods in Appendix D, as outlined properly by Standing, gave a recovery factor of about 13% oil, stock tank oil. And then there was a guy, Tom Dixon, worked at Phillips at the time. I think they published maybe one of the first papers, if not the first paper, where they modified their black oil treatment to include the gas that could, in a sense, dissolve into the stock tank oil that could dissolve into the gas as water dissolves into air, okay, and would condense out at the right conditions. When they corrected that black oil model, they got recoveries with everything else being the same, just changing the black oil tables, a 4% additional, almost 5% additional recovery factor. Went to between 17 and 18%. Well, 4%, 5% of 6 billion barrels is a lot of oil. So it really since then, since the 1980s, most of the engineering tools, not all of them, allow you and recommend that you use the modified black oil PVT methodology. Okay? Most of the reservoirs in the North Sea require it because they have higher pressure, they have a higher amount of gas content in the oil, certainly a good portion of them. And if you neglect that, then you'll be doing something seriously wrong. Some software products, unfortunately, still only allow you to use the traditional black oil formulation, ignoring this important contribution from the gas phase. Prosper, for example, the petroleum experts, the world's most used program for calculating pressure drop in pipe flow, does not allow you to use correct modified or complete black oil PVT formulation. Essentially all reservoir simulators, Eclipse, VIP, Sensor, CMG, all of the commercial reservoir simulators allow and generally recommend using the modified black oil tables. Well, in the book, the chapter 7 is dedicated to explaining what are the differences, how do you develop them, and in fact the methodology for coming up with the modified black oil properties came in a paper by which is discussed in detail in chapter 6 and chapter 7 in connection with the constant volume depletion lab test, which we'll talk about tomorrow. Okay, for gas is typically for gas condensates, but also for it can also be used and is often used for high GOR oils, volatile oils. Okay, and there's a guy who has been at Statoil. He was sitting here in 1979 when I came to Norway, and he was the top of the class in that group there, by the name of Stein Bøde Torp. He's now the head of, I think, drilling research at Ultvold. Stein Bøde and I published a paper, and in that paper we give a methodology for coming up with the complete modified set of black oil PVT tables. And that's discussed in detail in chapters 6 and 7. So that's kind of where we're going. The topic today will be the oil PVT experiment. We'll try to go through in detail the example laboratory test. Once we understand how the test is conducted, in the first hour we'll then go through and dissect number by number through such a report to understand where the numbers are coming from, how they relate to actual measurements, maybe they're calculated from unreported data and so forth. So we're going to go through that experimental procedure, and we're going to look at an experimental report, laboratory report, which someday you'll be probably looking at and wondering, what the hell were these, where do we get these data, what do they mean, and so forth, and then hopefully you'll have a better understanding of that because of this course. So that's kind of where we're going today, and then tomorrow we'll cover the constant volume depletion test, and we'll go through that in some detail tomorrow. Any questions? So that's kind of the game plan. And all of these measurements are leading towards normally coming up with a PVT model. We don't often use anymore directly the measurements from these tests as we used to up to about 1980. Up to about 1980, we either used the direct laboratory measurements in our engineering calculations. That was the most common way to do things. Today, essentially nobody does that. Essentially nobody uses directly the measurements in their engineering calculations. But instead, we use those calculations to create a more general PVT model called an equation of state. That model is then used to create these Blackwell tables. So that is today's work process. It's no longer using directly the laboratory data. Okay. I was fortunate enough in 1979, I believe, to be invited to a course, a 3-day course, I believe it was, by Core Laboratories in Stavanger. And I think it might have been my first visit to Stavanger, which was kind of nice too. And in that course, it was 1 day on PVT and 2 days on petrophysical properties, permeabilities, capillary pressures, and relative permeabilities. And what was really, I'd already gotten into the area of PVT in the way of research at that time, and at least a little bit, and was very excited about both parts of the course, but mainly the PVT course. And back then, there was essentially only one commercial laboratory doing PVT studies, and it was called Core Laboratories. There's still a company called Core Laboratories, even though it's been bought and sold a couple of times. It's now, it's still alive, so to speak. And the guy who was teaching the PVT part of the course, his name is Phil Moses. Phil Moses was the head at the very top, and their laboratory was in Dallas. The main laboratory was in Dallas. It was Phil Moses, and this guy signed off on every laboratory report, essentially. So I knew the name from having looked at some of the early PVT reports on Equifisk and Albashell, what I saw when I first got here. So it was an exciting thing to meet this guy and actually him presenting this PVT material. And he made a comment during that 1-day session that Mez Standing, who you've heard about many times, who was here teaching this course and most of the reservoir and production courses, essentially all of them, for 2 years in 1973 and 74. He told the story about Mez Standing, who was the head of the PVT group for Chevron, which was back then SoCal. It was a big oil company. And every PVT report they had conducted was at Core Laboratories, if they didn't do it themselves, in his own laboratory in Southern California. And Standing was very particular about everything being done correctly, everything being reported correctly. When Standing retired, his group gave him a plaque, thanks for your 40 years of being here. And it had at the bottom of it said, "Bah humbug." Okay? He was a very, there's no joking around, just get it done and get it done right. That was the only thing, in a sense, that mattered to him. So this, Phil Moses told the story about Standing having made the comment to Phil that Core Labs was teaching courses that Standing's engineers, young engineers, were going to. And he said that, "Phil, if I ever send an engineer to your course and find out later that he doesn't know how to make this here, then I'm never going to send another person to your courses, and I'm not going to use your laboratory ever again." He said this is the most important thing that they should get out of the course when they go to the course at Core Laboratories. Okay? And that was because every PVT calculation made in reservoir and production engineering essentially was a translation of the laboratory tests that we're going to talk about today into properties that could be used in engineering calculations. Okay? Well, that maybe doesn't mean anything to you. It made a big impact on me, and that is why Standing's set of notes that he developed here and used at Stanford when I had him as a professor on this translation and understanding of these experiments is essentially verbatim copied and included in the book as Appendix D. Now, today is different in the sense that we don't use these data directly as they were used when Stanley was practicing engineering. So you have to have other understandings, and you still have to understand things, but it's maybe not as important, but it is still important. So that's why we're going to spend essentially all of today talking about this experiment and trying to understand the laboratory report. See, there was one other comment I wanted to make as an introduction to this. Maybe I'll come back to it later. So that's basically where we're going and why we're going to go there. I wanted to inform you about the next 2 weeks. The next 2 weeks I will be gone, so there will not be lectures. So that the topic of the black oil PVT formulation will be posted as lectures that I've given earlier, and you'll be asked to read not only the chapter 6, which is what we were talking about last week, this week, but also to use chapter 7 to help you understand those lectures. So that will be posted, and you'll be on your own, so to speak. The second week I'm gone, there will be an exercise that you'll be doing, and that we will talk about when I return. And then after I return, we will have, in a sense, a summary of all of the PVT things we've been talking about during the semester. And at that point, we'll make a transition into flow and material balance, more application of the PVT for gas systems. So that'll happen after I return. Okay, any questions about kind of what we're doing and where we're going? Okay. So we're going to start talking about the differential liberation experiment. And as we mentioned last lecture, this is only used for oils. And how do we know if it's an oil? Because the constant composition expansion test measured what? What did the constant composition expansion test measure that tells us that this is an oil? It tells us that the saturation pressure type is a bubble point. Okay? So that we have a bubble point and not a dew point. That's how we know that it's an oil. Once an oil, then we have to make the decision to use this test or the constant volume depletion test. And I would generally say that it's used for oils, and probably it can be used for any oil. But for various reasons, I'm not going to get into now, but if you have an oil that has a very high gas-oil ratio, a very light oil, then you may choose, it may be a better idea to use the constant volume depletion test instead of the differential liberation test. So I'm going to put as kind of a footnote that you'll probably always use this test for oils with, when I say gas-oil ratio, I can just say the simplest of all gas-oil ratios. You just flash it to standard conditions, okay? The single-stage GOR. Approximately less than or equal to certainly 1,500, probably 2,000 standard cubic feet per stock tank barrel. Maybe as much as 2,500. That would be divided by 5, a little more 5, maybe 375 to 450 standard cubic meters. Well, let's just say anything greater than that in standard cubic meters, something like that. So if it's less than, about 450 standard cubic meters, say 400 standard cubic meters per standard cubic meter, you can probably use the DLE. That's probably what your boss will tell you to do if you're a young engineer. If you're an experienced engineer, you'll have some either opinion or you'll be colored by your what you've been doing or what the company's usually doing. The simplest is that just order the DLE. What I'm telling you is that it might make sense to consider the constant volume depletion as an alternative if the GOR is greater than around 400 to 500 standard cubic meters per standard cubic meter. So what is the purpose of this experiment? Why are we doing this experiment? The purpose of the experiment is mainly to get properties of the oil and gas phases as a function of pressure at reservoir temperature. So basically it's to get the properties of oil and gas phases as a function at reservoir temperature as a function of pressure less than or equal to the bubble point pressure. Okay? That's the purpose. So what are the properties? The properties are essentially density of oil, density of gas, typically expressed as Z factor of the gas and its molecular weight or specific gravity. Okay? Densities are always important. Well, not always important, but likely they're important somewhere in the production system. Reservoir, production tubing, certainly. Flow lines. So but in the reservoir, the densities can be important for a number of reasons we'll talk about. We want to know the relative volumes, how much the oil shrinks. Okay? So we basically want to know the oil volume, and I'm going to call it shrinkage. How much does the oil shrink as gas comes out of solution? Okay? As a function of pressure. Then the question is, why is it shrinking? Why is the oil shrinking? Is it because the pressure is decreasing? Well, an oil where the pressure decreases, usually the volume expands, right? We're saying that the oil shrinks. Why does it shrink? Pamper me. Give me a little help. Why is the oil shrinking?
Because some of the oil goes into gas phase.
Yeah, because gas comes out of solution, the dissolution of gas. So the important question is, how much gas comes out of solution? Okay? So basically, how much volume of gas is released? This solution, whatever you want to call it, comes out of solution from the oil. Okay? And we need to know the properties of that gas, the properties of the gas, the density, we've got that. And we may need, and we may ask for the composition. This is optional. That means optional, okay? The gas composition. Why might we be interested in the gas composition? Because as that gas comes out of solution, it expands as a gas does. And as the lower the pressure, the more of that gas you get, right? It gains mobility. As the gas gains mobility, we're going to produce more and more of it. So essentially, the gas that we see at the surface it may be coming from solution, it may be coming from free gas. But the point is that the translation at the surface of those components that are worth, what was it, 20 to 25 times as much, keeping it in the liquid as letting it stay in the surface gas. So it's basically these intermediate components that are C3 to C6 that are potential components to extract from the gas and put it back into a stock tank oil. Okay? So these are gas liquids, in a sense. That's usually why we want these compositions of gas. But this is kind of optional. And then the final thing that is not optional, what is the property of gas and oil that we definitely need to have that's not on the list here? Fundamental properties to do any engineering calculation of flow.
Viscosity.
The viscosity of the oil and the viscosity of the gas. They have to be there. Measured or calculated based on measurements. So these are the data that we are going to extract out of this test. Okay? No questions? I think that's it. That's all that's on my list. No questions? Now, what we could do in the laboratory is we could say, well, how does the actual reservoir produce when it goes below the bubble point? Okay, that would be a natural question to ask. And then we could say, can the laboratory mimic that process in order to come up with these properties? Okay, so, option one, we're talking about experimental design, design of experiments, not the mathematical process of experimental design, but the design of the experiment. The option one for the design is to mimic the actual physical depletion process. Okay, so how does that work? Well, we've got this, my reservoir is a very simple thing. Okay? Okay. We take out material we're producing from wells. Okay, this is our initial reservoir pressure. The pore volume containing the hydrocarbons. 1, 2, 3, 4. We need to try to keep that more or less volume. This is our hydrocarbon pore volume, hydrocarbon pore volume. We're going to assume that that's more or less remaining unchanged. Now, that's not exactly true because as you deplete these reservoirs, the rock volume will what? What will happen to the pore volume? The pore volume will get smaller. And what will happen to the water that is here? This is our connate water. What will happen to the water has no mobility. As pressure decreases, it's a water liquid phase. What happens to the volume of water as you decrease the pressure? The pressure decreases as we deplete. What will happen to the water volume? It will expand. Well, at least logically. Okay? But we said with the oil is not expanding, at least below the bubble point. It is, if we go down to the reservoir pressure being equal to the bubble point, yeah, the oil is also expanding here. But you know, that oil expansion is what's basically being produced here. The oil expands, right? But it has to go somewhere because the volume is confined, it's basically constant. But now let's say, well, the assumption of hydrocarbon pore volume being constant, it's not quite right because the compressibility of the rock, the pore volume, I'm going to exaggerate, the pore volume is getting smaller, pore compressibility, and that water volume we think is going to expand, and that's a correct assumption. I will make a comment, though, that in Chapter 9, if you read Chapter 9 on your own because you have no social life and you don't understand what's going on at UCA or you're already done with it, Chapter 9 talks about the fact that the water, because it's in equilibrium with this oil that contains methane and CO2 and ethane, God, nature, the thermodynamics, those components, methane, CO2, and propane and so forth, are actually found in the water. The water phase has solution gas. Okay? Yeah, that's just, you can't get away from it. So, in fact, as the pressure drops in that water, some of that will leave because of the new equilibrium. Probably will leave because those components would prefer being elsewhere in the oil phase. So now you've got this water that's, yeah, it's expanding. If it was a pure water, it would just expand on the pressure reduction. But then I'm saying, well, but now it's losing mass, okay? Okay? Because that water is actually saturated with components in the oil. But what you find in Chapter 9 is that, in fact, the expansion due to compressibility will win over the loss of mass. So the water volume will actually expand. Okay?
But when you deplete the reservoir,
Yeah?
does that mean that the pore pressure increases?
No. No, the pressure in the fluids will decrease. Yeah, the pressure in the fluids will decrease. The difference in the pressure between kind of the overburden pressure and the fluids is getting bigger. But the fluid pressure will always decrease. So what happens to the water is the water does in fact expand. But it expands into a smaller pore volume, right? So its saturation is actually, now we're in reality, the true pore volume, which I'll do in red, the true hydrocarbon pore volume is getting smaller, but not by very much. Okay? Not by very much. What do you mean, Curtis? Excuse me? What does not very much mean? You guys need to be a little bit curious. Well, for the purpose of what we're doing, it's not very much. It's maybe 1%, maybe 5% if it's a very high pressure reservoir, 5%. We're going to neglect it for the purpose of this. But 1 to 5% could mean a lot in other situations. Okay? Because in essence, the recovery factor, the percentage of oil that you produce out from here to here is exactly equal to that rock compressibility, the water compressibility, the oil compressibility, averaged in a correct way, times the pressure difference. Okay? And that can be 1%, can be 10%. If it's highly undersaturated pressure like crystal. Okay? So going from the reservoir pressure to the saturation pressure, you can produce a lot of oil. And that recovery is essentially given by the total compressibility times that pressure drop between initial pressure and saturation pressure. So in that case, it does make a difference. Okay, so when I say not very much, I'm saying in connection with what we're talking about the laboratory doing, mimicking the actual process. The fact that we lose hydrocarbon pore volume 1 to 5%, we're going to ignore it, good or bad. Okay. So I'm going to redo this picture. I'm going to get rid of all of the reality. I'm going to bring it back to, and I'm going to say that the hydrocarbon pore volume remains the same. Then we go to a new pressure. Okay. That's below reservoir pressure, below the bubble point. And then what happens? Well, what happens, I'm going to do it in kind of two steps. In reality, what happens is that you get kind of gas, before you take anything out, the total volume will expand. We're not going to let it expand because we're going to take something out. But what we take out, it helps to kind of, so this is before taking it out. So what we're going to get is that we're going to get some gas evolving. We're going to have some oil that's left. Okay, oil and gas. And what we could do, if we, if we're going to figure out in the reservoir, well, in the reservoir, we have to take out something to get back to this volume. Okay? So we have to take out something. What is that being taken out? In other words, how much gas do we take out and how much oil do we take out to bring it back to this pore volume? Well, we could take out half of the gas, right? Or we could take out the lower part of the oil, leave the gas. There's an infinite number of ways to do that, okay? So tell me, how do you think nature, because nature doesn't go to my classes, I'm sure nature, God, whatever you believe in, is off doing something more interesting than sitting here. How does nature decide what to take out? Well, let's just think in terms of PVT only. Gas is less viscous than oil, at least an order of magnitude, right? So intuitively, you would think the gas is going to want to flow faster than the oil, right? So what actually is going to happen is that you're going to have, do it in color-coded. You're going to have the gas flowing flow out from the reservoir. Okay? Well, that's controlled by what is the gas mobility and what is the oil mobility. That's the term for mobility. Okay? And as you'll learn in other courses, if you haven't already learned it, I think Torstetter or somebody will teach you this, is that this is the ratio of the permeability of the gas divided by its viscosity. It is Darcy who's telling us what the mobility is. This is Darcy's law. Okay? And for the oil, it's the permeability of the oil over the gas, over the oil viscosity. How many knew this? Okay? All right, good. So next time, help me. Okay, help me out. Now, the permeability of gas is the absolute permeability, which is the same for both phases, 100 millidarcies or whatever, times what? The relative permeability of gas, which is a function of what? The saturation of the gas. Okay? I'm going crazy here, trying to keep you guys entertained with colors. You know, I know I shouldn't do it. This is like that. And the gas relative permeability is a function of the gas saturation. Okay? Or the oil saturation. It doesn't really matter. There's just two saturations controlling this. We're going to ignore the water saturation. And the oil is the same permeability times the green KRO, which is a function of oil saturation, over oil viscosity. Okay? Well, oil saturation is just 1 minus gas saturation minus water saturation. So effectively, if you have one or the other, you can say both of them are a function of gas saturation, for example, okay? Or both of them are a function of oil saturation. It's basically the same thing. The point is that we need to know what is the volume of the gas phase and what is the volume of the oil phase, and that is what we find. This is basically this is kind of a constant composition expansion where we get the gas volume, the oil volume, divided by the total volume. That gives us approximately the gas saturation and the oil saturation. Okay? And what you'll find is that for a given phase, be it gas or oil, that this is approximately given by that phase saturation to a power n, and that power n is a constant for that phase. And that power n ranges somewhere, if God is nice, if you're lucky, okay, it might be 2 point something, and if you're really nasty, if you're not behaving, Mother Nature gives you something that might be as high as 4 or 5. I'm going to say 4.x, okay? It's a highly nonlinear function of saturation. That means as the oil saturation drops because the gas is coming out of solution, the oil is shrinking, the oil permeability will not go, let's say that the oil saturation goes from 90% to 80%. The relative permeability does not go down a factor of 10%. It might go down a factor of 50%. And the gas saturation goes from 0 to 10%. The gas mobility goes from 0 maybe, well, to some magnitude, 10%. 10% of the absolute permeability. So what happens is that as the gas comes out of solution, this thing is shooting up and this thing is going down. Okay? So what would happen in the first stage here is that, well, maybe the very first stage, you'd get more oil. The oil mobility might be higher than the gas mobility in this first stage, maybe not very much. Okay. But as you release more and more gas, you get a higher and higher gas saturation. And way over time. You get excited about stuff, and you guys don't say stop. Okay, so let me just finish the thought process here. The first thing is that these are the relative permeability are rock properties. And we don't know the rock properties when we do the PVT experiment. Even if we knew them, we would know that the exponent might range from 3 to 4 for a given reservoir. So there is not a fixed relative permeability relation. And if you tell the laboratory, well, go drop it down, look at the volumes, here's the relative permeability relationship, you would need to know the viscosities, okay, ahead of time to find out how much gas to take out and how much oil to take out. Do you all see where this is going? It's too complicated. You don't have enough information. You cannot mimic the actual physical process because the actual physical process is not known. So it's not an alternative for the laboratory to try to do this, take out so much gas and take so much oil. All right? It's not an option. Okay, so it's not feasible. Okay. So we got to have a second option. And maybe two options. Okay. Now you guys having as much fun as me. Is that why you didn't tell me it's 10? See, I forgot my watch. So I'm totally, I keep going for 3 hours. We're done. I can go for 3 hours. I'm old, but not that old. Particularly you get excited about stuff. Okay. And the fact that you understand what I'm talking about, the fact that this amount of gas coming out of solution affects the gas mobility. The gas mobility, the higher it is, the lower oil recovery you have. The lower oil recovery you have, the less money you make, and the less money you make, the lower your salaries. That you understand, right? Okay, it is that simple. So if you understand and connect the dots, then you'll realize that, yeah, PVT does actually have some kind of bottom line effect. Okay? That's why I get excited about it. Okay. Anyway, we'll take a break now and get cited in 15 minutes.